So number 14 then, from the 2022 mechanics paper, 7-mark question here for, now acceleration is given in terms of the distance x here. So normally whenever you see that, you think of that connection then, that a equals v dv by dx, because that's just dx by dt, they cancel out dv by dt. And then you'd be using that in an integration. However, what does it say? First part. So for this expression for a, calculate the displacement when the particle reaches its maximum speed. Well, the thing there would be, you can see what that looks like. That's just an upside down parabola. So that's the acceleration looking like that in terms of x. Only when x is 0, it's got a value, so it'll be like this. Oh, missed it. So if that's the graph, I need to change this pen, x, and that's the acceleration up the way, then it's going to be accelerating until it gets to this point here. Doesn't matter that that's a maximum. Those are still positive accelerations. So as long as you've got a positive acceleration, you're still speeding up. So in order to find that, you need to find this value of x here. That's when a reaches 0. So I want to know when a reaches 0. I don't want this negative value here. So you just want to solve that equation. I think I'll just write that the other way around. So you're really solving 2x squared minus x minus 15 equals 0. Well, that must be 2x and that must be x. And then you've got 3 and 5. So I want to make a difference of 1, so I'll have to do 2 3s or 6. So 3 and 5, negative in the middle, minus the 3 plus the 5. So that's going to give you 2 answers. Either negative 5 upon 2, so that's before it started, or the one that you want, x equals 3. So that's the answer you want. So that means that you've got the maximum speed at x equals 3. And it's all given in that, so that should be 3 meters, I suppose. So the first part was state the condition for x to give the maximum speed. I've just rearranged it, they've just left it the original way, and then actually finding it. Part B eventually says, calculate that maximum speed. Well, you could get that in one go just by using this connection here, a equals v dv by dt, over the appropriate values. And that would do it in one go, but it splits it up in saying this, first of all, calculate the work done, which sort of forces your hand, because if you've got to do this, then there's no point in doing it with that, which would be a quicker way, because you'll have to actually work out the work done. Well, work done is force times distance. Whatever you want to put down for work done, u or whatever symbol, I'll just put work done to begin with here. So the work done would be force times distance. So that'd just be fx. If it was all just a constant, but it's not constant, because that acceleration f equals ma is not constant. So that means you have to carry out an integration. So it'll be the integral of f dx, because f is variable, because the acceleration is variable. So that's going to be, now f is ma, but the mass was constant, so it'll be m, I should have put a 5 in, a dx, I'll put it in. So what have you got? You've got 5 times the integral, but at least you know the limits. It reached its maximum at 3, so how much work was done in getting to that point from 0 to 3 for x, and a is 15 plus x minus 2x squared dx. So putting that in gets a mark. Now just do it. So you've got 5 times, and your integral of that will be 15x, a half x squared, and that will be 2/3 of x cubed from 0 to 3. At least at 0, it's 0, so it'll just be all of them at 3. So this is the calculation. You're going to have to do 15 times 3 plus a half of 3 squared minus 2/3 of 3 cubed, and it'll be that minus 0, of course. So having that, integrating it, that gets a mark, and then the last mark's for this answer for the work done. So pressing the buttons gives you 157.5. So that would be joules for the last mark for the work done. And then in part 2 it says hence, that means using this, or otherwise, which would have been that, but that would have done instead of the whole thing, so I'll just have to do the hence. Hence, calculate the maximum speed. Well, that work was done in increasing the kinetic energy from its initial value to its final value. So that work done is going to be equal to the final kinetic energy, that will be a half mv squared, that was that v max, minus a half m times, and the initial velocity was 0 squared. So that's what's equal to 157.5. So that's that work energy principle. And the work that you put in increases the energy of the system. So it's increased its kinetic energy because it just stayed level. Now it's just a case of solving that. Well, that's just 0. So all I've got to do is take that m across and take that half across. So I'm going to have v squared will be 157.5 times the 2 divided by the 5, which comes to a nice 63, which means the maximum velocity would have been the square root of 63, if you want to just leave it exact, meters per second, or 7.937 and so on. So we call that 7.94 meters per second for the final mark. Now that part B could have been done if I didn't actually say or tell you to work out that work done to begin with, just by using that expression there. That's the one that just comes from A is dv by dt. So if you just introduce some other differentials, make it by dx and then multiply by dx, that cancels that out. dv by dx by v. Just by using that, v dv equals a dx. You could have done it without needing the mass. You could have done it by the kinematics, it's called, instead of the kinetics. So what you would have here would be just integrate that up. So you'd have the integral of v dv from 0 to whatever v max is, would be the integral, and the x's went from 0 to 3 of 15 plus x minus 2x squared dx. That would have been, well, there would have been 5 marks for doing this. I don't know how they would have been put down, because this actually applies to the whole lot, not just to the second part. In which case you've got a half of v squared from 0 to v max would be 15x plus a half of x squared minus 2/3 of x cubed from 0 to 3. Well, that's going from 0, so that's just going to be a half of v squared will be, and there's that same calculation that you did before, 15 times 3 plus a half of 3 squared minus 2/3 of 3 cubed. The only difference being you didn't have to multiply it by a 5 minus 0. And then when you did that and multiplied it by 2 and did the square root, it'd be the same as before, the square root of 63. But you wouldn't have done that because you already had to do all of that in part 1 by finding the work done. So there was no point in just replicating it by doing an otherwise method. So you're sort of forced into using work done equal to change in kinetic energy.